What's up, guys? Let's discuss the most popular API architectural style, which is REST. So let's get into it. So, representational state transfer, otherwise known as REST. So let's talk about the motivation that caused the creation of REST. So back in the day, the web was on the way to collapse since the user's traffic was outgrowing the capacity of the internet's infrastructure. This forced software architects to design an efficient web architecture to make the web flexible, performant, and scalable. So the REST architecture was proposed, and it plays a vital role in designing scalable systems. So let's talk about REST. REST was proposed by Roy Fielding in 2000 to solve the web scalability problem. The scalability problem could be directed by certain key constraints, and these constraints act as a backbone for designing REST APIs. So, the pragmatic approach to satisfy the following constraints being client server, cache, stateless, uniform interface, a layered system, and code on demand. So, these are all constraints that we are trying to address with REST, and we'll talk more about these constraints. So, client server. Client server is the most commonly employed architectural style for network based applications. A server component that provides several services listening for a request for those services. Client communicates with the server via the internet, waits for a request to be processed by the server. The request is either fulfilled or rejected and communicated back to the client. In this scenario, there's a separation of concerns, and the core principle that focuses on the client server constraints. Server component should be simple through functional separation. It's consolidating all user interface features into a single client component, and components can be evolved separately as long as the interface stays the same. So now let's talk about the cache constraint. An intermediary component. So a cache is an intermediary component between the client and server that contains the response to an earlier request. Cached responses are used for equivalent and identical requests instead of directing requests to the server. The user perceived performance is improved using a cache. The constraint requires that response data be explicit or implicitly marked cacheable or non-cacheable. So the trade-off the trade-off with the cache constraint is that it can reduce reliability and consistency if stale data in the cache varies a lot from the server or from the data received in the direct request to the server. What is the approach to check the validity of the data in the cache? So there are a few ways to do this. One is to use the expires HTTP header in the response, and that would determine when the page needs to be fetched again, right? And you can also use some heuristics. If a page is not modified in the last year, indicated by the last modified HTTP header, it's improbable that it will change in the next hour, right? And you can use conditional get. Through this request, the server will return a short reply if the cached page is still valid. Otherwise, the server will send a complete message, right? So here we have an example of a REST request, HTTP request, or a response, I mean. So here we have our if modified since header, right? And this is our conditional get request. If modified since HTTP header makes the get request conditional. So basically, if it's been modified since, it will send you a new version of that cache data. So it's stateless. So this constraint refers to how no session state is allowed on the server. So this should be kept on the client, and each request from the client should contain all the information for the server to process. So this improves the following performance measures. Reliability is increased since the server can recover from partial failures easily. There's no data lost, for the users that are calling the server, right? Scalability is improved since no user data is actually stored on the server, and this frees the resources for other incoming requests. And visibility is improved since the server does not have to look for extra information rather than the data in the request to determine the request's nature, right? So all the information the server needs is in that request. If the request needs to get data from the database, it will contain all the necessary information to make that database query. So the trade-off is that it might reduce the network's performance, right? Because in this case, if it's stateless, that means we're going to have a little bit more headers, more information in our requests, right? So this could impact the network's performance. So let's talk about the uniform interface constraint. So a system is composed of several components, and for it to work, the components' interaction should be directed by a uniform interface. The exchange of data should be standardized between components. The disadvantage is that it might degrade efficiency since the information has to be transferred in a standardized form rather than a form required by the application, right? So, all different kinds of clients here. They use the same interface when communicating with the server, right? The following architectural constraints are proposed to guide the behavior of the components, such as identification of resources. In REST, the abstraction of information is a resource. Resources can be images, videos, documents, etc., and these resources are addressed by a unique identifier called a Uniform Resource Identifier, or URI, right? There's also manipulation of resources through representations. So representation of data is the sequence of bytes and the relevant metadata. Clients can manipulate the representation of resources. The same exact source, right, can be represented to clients in many different ways, right? If you called Google from Insomnia or some API tool, right, you'll get back like a HTML file in like text or something, right? But if you do that same request in a browser, it'll display the actual HTML and everything, right? So, yeah, as an example, a web page can be rendered as an HTML page in browser or JSON format in a console program. There's also self-descriptive messages, another constraint that ensures uniform interface between different components. A self-descriptive response message that contains all the information the client needs to understand. For example, we have a 200 OK, which indicates that the successful execution of the client's request, right? And also hypermedia as the engine of application state. A client can request information dynamically through hypermedia. Hypermedia is a non-linear media of information containing different types of resources, such as images, videos, hyperlinks, etc. Hypermedia is a non-linear media of information containing different types of resources. And now let's talk about the layered system constraint. The layered system constraint imposes an organized layer or organized group of layers between client and server. And this enables client-server communication to be intercepted by other essential components to make the communication easier, secure, and directed to the intended servers. The layered approach enhances the decoupling across multiple layers by making it visible to only the adjacent layers and hiding it from other layers, right? For example, we have a client, we have our group of clients, right? Then it calls a web server, and that server calls a load balancer, and then that load balancer routes it to an appropriate server, right? So it's done in layers. The layered system also improves the evolvability because each layer can be modified or added with advanced functionality without affecting the other layers. Reusability because the existing components can be reused in one form or another instead of reinventing or creating a layer from scratch. An example of a layered system is adding a proxy as well as load balancing and security checking components between the client and server communication. And one drawback is that the requests or responses may have to traverse more hops, which does add latency. And there's also code on demand. So this constraint enables web servers to send executable programs or code to the client, such as plugins, scripts, applets, and so on. Code on demand establishes a technological coupling between clients and servers. The client must understand the code downloaded from the server. Therefore, this constraint is optional. For example, certain applications require additional plugins to be installed on the client side, right? Like scripts or other things. The major advantage of the code on demand are it makes it extensible. So the client's extensibility is improved because it has the independence of how certain things can be done. Performance, the user's perceived performance is improved because certain things happen locally on the client side instead of regular interaction with the server. One drawback is that scripts sent from the server may contain malicious code. Another drawback is that monitoring systems may be unable to track the request's intent due to the server sending code instead of data. So, in conclusion, adhering to all 6 constraints is only possible in an ideal scenario. Some of the constraints are conflicting, right? So if we conform to the stateless constraint, we can achieve visibility, right? However, at the same time, using the code on demand constraint reduces visibility of the full nature of the request. API designers should follow the maximum possible constraints while designing a RESTful web API. So here's an overview of all of our constraints. So we have our client server. So the features are it improves the evolvability of clients and server, right? It increases scalability, but the drawback is an enormous number of user requests can overload the server. Network disconnectivity may cause an interruption in our service, right? We also have a cache. This reduces latency by storing data on the client side, but the drawbacks are it reduces consistency if stale data in the cache varies considerably from data in the recent responses from the server. There's also stateless, right? So this improves the reliability. It increases the scalability in terms of incoming requests, and it also improves the visibility of requests for analysis, right? But the drawback is it reduces the network performance by sending repetitive data in a series of requests. So we also have uniform interface. The features being it improves independent development of components, right? It smoothens the interactions of entities. It improves evolvability of the components. A drawback of this is that it degrades the efficiency and flexibility because the information has to be sent in a standardized form rather than whatever is required by the application, right? And then we also have a layered system constraint, which improves the evolvability and reusability of different components, and it enhances decoupling of the components, right? But the drawback is it reduces the performance by increasing the processing overhead of many different layers, and high security is needed at each layer to keep the communication secure. And code on demand improves our extensibility. It increases performance, right? But the drawback is that it reduces the trackability of the requests by the monitoring systems and may sometimes compromise the security of the client, right? So let's do a quick quiz. What's the difference between REST and HTTP? So REST is a web architecture style that proposes some constraints that should be used to design web or mobile applications. HTTP, on the other hand, is the protocol, or in simple words, a method that enables us to achieve the constraints proposed by REST, right? So hopefully you learned something. Thanks so much for watching. I'll see you in the next one.